Hello guys and welcome to my YouTube channel. So today I want to be discussing the May-June 2024 question paper for 2 for physics, and the question paper is 2 hours long actually. It's a very recent paper. Let's get to it. The first question, we've been asked to define the radian. What is a radian? So imagine you have a circle, right? If you were to draw any circle, and if you were to take the arc length, so that's the arc length, right? And you were to take the radius for that same circle. If the arc length and the radius are equal, we say the angle that formed that certain situation, a radian. So in simple terms, a radian is just, right? So that angle that we have subtended at the center of a circle by an arc length that is equal to the radius, we call that angle the radian. Okay, moving on now. Move on to the next question. We have a circular metal disc that spins horizontally about a vertical axis. So we have a metal disc, right? A disc, something that just rotates. And we have a piece of modeling clay. So we have modeling clay, that's modeling clay, and we've sort of attached it onto that specific disc. As you can see, we have 1.2 centimeters from the edge of the disc, but 9.3 centimeters from the center to the edge of the disc. So I've been asked to show an arrow labeled V the direction of the velocity of the modeling clay. Now, whenever we have these specific kind of questions, we really want to understand what is simple harmonic motion. We really want to understand what is circular motion. So in these kind of questions, circular motion will sort of be the motion of an object with an acceleration that is directed towards the center, but the velocity itself will be at a tangent to the motion of this specific thing. If we're asked to draw the velocity at this point, what I'll just do is just draw an arrow like this, right? Just indicate the direction in which it's going to be moving at. And that's it. You have your 1 mark, right? An arrow labeled A, so just label it V and just, obey what they're saying, right? Label your arrow V. Then an arrow labeled A showing the direction of acceleration of modeling clay. So sort of like in this northwest direction, like so. So our velocity is always at a tangent to the circle itself, and then my acceleration is going to be labeled A, which will be over there. Okay, makes sense? The metal disc has a radius of 9.3 centimeters. So if I have a disc and as the disc is rotating itself, it has a radius of 9.3 centimeters. That's from the center to the edge. The center of gravity is 1.2 centimeters from the rim and moves with a speed of 0.68. So I want to ask myself, what am I given and what am I supposed to find? I'm supposed to find the angular speed omega, but I'm given the speed of 0.68. That's the linear speed. I'm also given the radius, well, kind of, because I know this is 9.3 centimeters to get to the edge. I know it's 1.2 from the edge, and the difference of that is going to be your radius. So what I can just do is relate all of these variables by an equation. What equation, guys? Right? Let's think. I'm given V is equal to omega multiplied by r. That's the equation that I can relate these 3 things that I'm given. But my radius is just going to be 9.3 subtract 1.2, so that I can be able to get my radius as that specific thing, and that's going to give me an answer of 8.1. Okay, that's my value of r. So if I want to find my omega, it's just going to be my velocity 0.68 divided by my r, which is 8.1, 8.4, right? Rounded off to 2SF because the smallest significant figures here have also 2SF, so it's going to be 8.4. Okay, I'll move on to the next question. Calculate the acceleration A of the center of gravity of the modeling clay. Whenever we have circular motion, I know my acceleration is just going to be equivalent to omega squared multiplied by r, or omega A is equals to v squared divided by r. That's going to give me an acceleration typically of 5.7. Move on to the next question. We've given a second piece of modeling clay. That is attached to the disc. So I had the first piece of modeling clay, I attached it. Then the second piece again of modeling clay, and I also attached it. But this one has a slightly bigger mass. It's bigger. If I were to weigh these 2 ones, right, the second piece has a bigger mass. And I want to compare how these 3 quantities vary, right? Angular speed, linear speed, acceleration. So in order for you to understand questions, you have to understand where they come from. What is omega? Just ask yourself, what is omega? So imagine you have a big circle, right? Omega is the rate of change of displacement, angular displacement, let's put it at that. So what is angular displacement? It's an angle that you subtend, So angular speed is the rate at which the angular displacement changes. The angle that you're going to form is going to change. Every single point that will be present at any given point has the same omega. Does it sound a little bit tricky? Let's try it out. So let's put a line like that, right? We'll put a line like that, and let's put points. 1, 2. All of these, as the circle is moving around, are completing the exact same angle. It's just that the one at the top will travel greater arc length, then the one here closer to the center is travel a smaller arc length. But the angle that they all make is still 45 degrees. If it's 45 degrees, the angle is still 45 degrees, guys, when they are moving. So what's going to cause them to have different distances that they move but still make the same angle is their speed. One is going to be slower than the other. The one closer to the center is going to be slower than the one moving afar. So the difference between these two is the linear speed. The one closer to the center is actually a smaller linear speed. But the omega is just the same. The angle that they make, the rate at which angular displacement changes, is just going to be the same, guys. Then the acceleration is actually having a certain relationship. Remember, I said omega is constant. Okay, so I know a relationship that tells me that A, right? That tells me that A is equal to omega squared R. So if this, guys, if this is constant, what essentially I can then do is sort of, after I've made my relationship, see a relationship between A and R, right? I can see they're direct proportional. So for the second one, it has a smaller radius. Okay, so it's going to have a sort of slightly smaller acceleration, right? Smaller radius, smaller acceleration. So I'm going to put a smaller acceleration. I hope that makes sense, right? Same angle must be completed, so the rate of change of angular displacement is going to be the same. But one is going to move faster because it has to travel a longer distance, and then closer to the center, it has to travel a smaller distance because the distance needed to form that angle is actually pretty small. But the acceleration of one is going to be lesser because it has a smaller radius and it also has a smaller speed. Hope that makes sense. Okay, move on to the next question. With reference to thermal energy, state what is meant by two objects being in thermal equilibrium. What is thermal equilibrium? Well, objects will just be at the same temperature and there is no net transfer of thermal energy. Right? Hope that sort of makes sense. Okay. Two cylinders X and Y each contain a sample of an ideal gas. Now the samples are in thermal equilibrium with each other. X is the volume of this and contains these number of moles at a pressure like that. Y is the volume of that, contains gas at this particular pressure, and data for that has been given. So I have two cylinders. Let's put them. Cylinder A, cylinder X, and cylinder Y, and they both meet that certain criterion. So you want to show that the gas in cylinder X is 234 degrees. So the gas in cylinder X is a temperature of 234 degrees Celsius. What am I going to do? Okay, so essentially, if I look at this, I'm given the number of moles. Okay, ask yourself, what are you given? You're given the number of moles, here you're given the pressure, and here you're given the volume. What is one equation that links all of these things together? Right? What equation is coming to your mind right now? Just say it out. Right? PV is equivalent to nRT because it links pressure, volume, number of moles, or you know it because you can find it in your data booklet, and the temperature. So the temperature, so I first write PV is equals to nR times T. So my temperature T is just going to be my pressure being 1.20 times 10 to the power of 5 multiplied by my volume 0.0260, all of that divided by my number of moles, which is 0.740 multiplied by 8.31. And if you are wondering what 8.31 is, that is R, the molar gas constant, R. Let's put it at that. And if I want to convert these to degrees Celsius, all I just have to do is just say 507 minus 273. That's going to give me 234 degrees. Hope that makes sense. Okay. Determine the number N of gas, number of molecules N of gas in Y. So I've cylinder Y, right? And I want to find the number of molecules. Right? How many molecules do I actually have that make this Y? So I ask myself, what am I given? Right? What am I given? I'm given pressure, P. I'm given volume, V. What is some of the thing? What is one equation that links these two things together? Again, we have another equation, PV is equals to N, big N, for number of molecules, NKT. So that's what I can use, right? So if I come here, I can just essentially say PV is equals to big N, small letter k, and T. Okay? So if I want to find N, it's just equal to PV divided by K multiplied by T. And remember, these two things are in thermal equilibrium, gas X and Y. And what makes me say that? I've been told that they actually are in thermal equilibrium right here, guys. Okay, so the temperature has to be the same. There's no net transfer of energy, and they have to be at the same temperature. So if I'm here, my pressure for Y is going to be 2.90 times 10 to the power of 5. Okay, so 2.90 times 10 to the power of 5 multiplied by 0.0430 for my volume. I'm given that, guys. And my value of K is just going to be 1.3878 times 10 to the power of 24. So it's 1.78 times 10 to the power of 24. Hope that makes sense, right? I'll move on to the next question. The gas in X consists of molecules. So I have X, right? Cylinder X. And it has certain gas molecules. So that's cylinder X. And those are the gas molecules that are present in that. And the molecules have a mass that is 4 times the mass of the molecules in cylinder Y. So cylinder X, cylinder Y. And the molecules in cylinder X actually have 4 times the mass of molecules in Y. Now I want to explain how the root mean square speed of the molecules in X compare with the root mean square speed of the molecules in Y. So I'm going to ask myself 2 questions, right? So whenever you're given these kind of questions, ask yourself, what are you given? And what are you asked to do? So in this question, I've been given the root mean square speed of the molecules in X, and I've been told that gas X consists of molecules that each have a mass, right? That is 4 times the mass of a molecule. So I have mass that's 4 times, and I want to explain how the root mean square speed of the molecules compare. Okay, so what relates mass and root mean square speed? That's going to be my question, right? And you might be wondering, well, how do I connect them? Well, remember kinetic energy. What is kinetic energy? Kinetic energy is just 1/2 mv squared. But what's root mean square speed? Well, molecules move, right? They're going to move with a certain velocity. So it's going to move and whiz about, right? And each and every molecule has its own peculiar, unique velocity. Could be different. One could be greater, one could be less. It can't always be the same. So there's a way in which we can find the overall mean square speed of each and every of these molecules. So we square each and every velocity, we add them up, divide, and do certain computations that are going to give us the root mean square speed. So overall, if I have a gas sample, the root mean square speed tells me the overall speed that each of the molecules is supposed to have, sort of like an average speed. Right? You have people in a race, you find out the speed of this guy, the speed of this guy, the speed of this guy, add that up, divide by the number of people, and you sort of get the average speed that each and every person in that race is working with. So that's the root mean square speed. So if I want to find the total kinetic energy of all the particles that are present in a specific gas sample, I know that for one of the molecules, right, for one of the molecules, the kinetic energy will just be 1/2 mv squared, and I can assume that it's moving at the root mean square speed. And root mean square speed is just C RMS, okay? And sort of the mean square speed on its own is just represented by this, right? Like so. So my EK would just be equal to 1/2 m, right, C squared, like this. So I sort of have this little relationship trying to get established. So, but remember, X and Y are the same temperature. And temperature is associated actually with kinetic energy. Right? Temperature describes motion. Right? If you have a high temperature, the particles themselves have a high kinetic energy. So if you're at the same temperature, you're going to have the same kinetic energy. So for X and Y, EK is the same. Right? So for X and Y, EK is the same. Okay? Does that make sense? So I want to compare what happens to M and what happens to C squared. So the first point, I just have to mention how the kinetic energy relates to the temperature. So the first point that I can mention, I can just say the kinetic energy is proportional to the temperature. And I know this is true, right? I know if the kinetic energy is a certain value, the temperature is also a certain value, because temperature by its nature describes and tells me information about the kinetic energy. That's the first thing that I sort of have to mention. So now I want to figure out, okay, what's happening to the root RMS, what's happening to the mass. So there are multiple ways you can go about this, multiple ways. So we're just gonna look at this relationship here, establish a sort of trend, if you may. So 2ek is going to be equal to mc squared. Don't worry, I'm just making things subject of formula. Okay, so I put mass over there, right? I have 1 over m. 2ek should be equal to c squared. Okay, so you can sort of see a relationship between 1 over m and c squared. So I can say 1 over m is directly proportional to c squared. Look at that relationship, that beautiful, nice relationship. Okay, so I want to find what's going on, what's happening here. So from this specific relationship, I can see that the RMS itself, the RMS, so if I were to make the RMS a bit of formula, just take the square root from both sides, the CRMS will be directly proportional to the square root of 1 over the mass, right? I just took a square root on the other side, and I took a square root on this side, like so, guys. A square root on this side, a square root on this side. I hope you're following, right? I started off by EK, the equation that describes one molecule, right? If it's not making sense, just comment it out, and I'll be happy to answer that. So you start with the EK, and your relationship, EK is the same. You want to establish a relationship between the mass and the CRMS, and I took 1 over m and c squared to find CRMS, square root on both sides. So that's my relationship between CRMS and 1 over m, and I'll just state that. So first, look at your variables, right? You're given mass, you're given RMS. Look at the relationship. Use an equation, guys. That's going to tell you the relationship between those two variables. So the equation itself will tell me that the root mean square speed, right, is inversely, right, proportional to mass. Simply put, CRMS is like so. So it's inversely proportional to the square root of mass. Right? So if we take the square root of mass and CRMS, they're inversely proportional. So what's going to happen? If I have 4 times the mass, which is over here, so instead of having this specific value, it is going to be 4m. What's going to be my effect on CRMS? Okay, I'm sort of trying to figure that out. So I can just establish a trend, right? And just say, for the first instance, let me just put a constant here. It's just going to be CRMS should be equal to the square root of 1 over 4m, right? And then I just put a constant k over there, right? Because it's an equation that I've just created. Okay, I can take out this 4 outside of the square root, that's just half, right? Because it's root of 1 over 4 times the root of 1 over m, and 1 over m, right, is equal to CRMS. This is for y, because this is for x, which is the mass, that is 4 times the mass of y. So this is for x, right? But I already know that root of 1 over m alone is already for y. So CRMS for x will be equal to 1/2 the CRMS for y. And that's a trend, a relationship that I've established. So guys, follow the steps. I had an equation that I was using to find the relationship between variables. The rest is mathematics. It's just create a constant k, create an equation, take out the quarter, becomes a half. So the CRMS for x is half the CRMS for y. Hope that makes sense. If it's not making sense, again, just comment it out and I'll be happy to respond. So the root mean squared speed, that's it. I've made the deduction, right? Start with what you have, figure out the relationship, the equation that links all those things. Just take your conclusion. That'll be it. Moving on. State what is meant by the internal energy of a system. Okay, what is internal energy? That's what we want to figure out. Every gas that moves around here has potential energy, right? It can be electric potential energy. It can be any potential energy that you want to describe. Every system that you have is going to have certain kinds of energy, but internal energy is the sum of the potential energy and the kinetic energy of random motion of particles. So particles, they're always in random motion. Never leave out the random motion aspect. And because they're in random motion, I want to add the kinetic energies of these specific particles, and I want to add the potential energy of these specific particles. What is kinetic energy? It's the energy that is associated with the speed of these molecules, right? They have a certain speed, arises due to a certain temperature because they have a certain energy, and that's going to be the energy that I'm adding with the potential energy. I hope that makes sense, right? So now I've been told that with reference to molecular kinetic energy and potential energy, describe and explain how the internal energy of the system changes when a gas is heated at constant volume so that its temperature increases. Okay, so guys, I want you to understand something here. You've been given restrictions. Very important. You've been given restrictions, right? You've been told that U is equal to EK plus EP. You add the kinetic energy, you add the potential energy, you get your kinetic energy. Now remember, like I said, kinetic energy is related to temperature changes. So as the temperature increases, the kinetic energy is going to increase, right? Because the kinetic energy tells me the overall kinetic energy itself that the molecule actually has. So temperature increases, that's sort of what happens. And then the next step is in relation to potential energy. You've been told, talk about kinetic energy. You've been told, talk about potential energy. How are these two things changing? So that you can then overly comment about the internal energy. So whenever a question gives you potential energy, I want you guys to look for separation. If the separation between the molecules increases, the potential energy will increase because they're far away. They have to store energy. They have to do energy in order for that to happen. So the potential energy is going to increase. If the molecules are closer to each other, potential energy decreases. If there's no change in separation, there is no change in potential. So in this specific case, there's no change in separation, so there's no change in potential. Has increased, and PE is just constant. Overall, my internal energy therefore increases. That's it. I have a wire, and I'm stretching that wire within elastic limit so it doesn't become inelastic at a constant temperature. Come on guys, constant temperature, what does that mean? Come on, it means that the kinetic energy remains constant, because if there's no change in temperature, then there's no change in kinetic energy, temperature. Okay, so temperature is constant, right? But if you have a wire and you stretch it, right? You take one point and you stretch that wire. What's going to happen is that the molecules themselves are going to start moving apart before it breaks, right? Before it's doing elastic limits so then come back. But as I'm doing that, the separation between the molecules itself actually increases, right? Because you're separating something and the separation itself is going to increase. So if I were to put that, I'll just say separation increases, right? Now think of this, right? My potential energy has increased. My kinetic energy is actually constant. So what's going to happen to my internal energy, guys? You tell me. So internal energy would therefore increase, right? So guys, I need you to think on your own. If a question comes and it says the wire is compressed, what's going to happen? Separation decreases, potential energy decreases, constant temperature. Okay, move on to the next question. With a block M that is oscillating on a spring. I have a spring and I have a block. I start allowing it to oscillate. Oscillation is up and down. A complete oscillation is up, goes above, goes down, and goes back to its original position. That's an oscillation. So I have that occurring, and the acceleration A of the block varies with displacement x from the equilibrium position. So as it goes up and down, the acceleration itself varies with the displacement. Right? I hope that makes sense. Okay, let's look at the next question. The amplitude of the oscillation in 3y, the maximum acceleration is 2a. Explain how the figure shows the oscillations are in simple harmonic. Right? I would have preferred. Okay, so we want to show that the oscillations are simple harmonic. How do we do that? Now, what is simple harmonic motion? Right? It's a motion in which the acceleration is directly proportional to the displacement, but in opposite direction. We see opposite direction because there'll be presence of a negative sign. So how do you show proportionality? Proportionality is basically seen by a straight line graph that passes through the origin. There's no way you can see that things are directly proportional except for that. So I'm going to say, because I see a straight line that passes through the origin, that indicates that acceleration itself is proportional to displacement x, right? Because I have a straight line that's passing through the origin. But to prove that they're in opposite direction, as the acceleration is increasing and the displacement itself should also be in the opposite direction. So if I'm going like that, the acceleration will be directed towards the center, but the displacement will be directed towards that side, right? Showing that these two things are particularly in opposite directions. So I can say that and say the negative gradient then shows me that they're in opposite directions. So negative gradient, because you can see that a negative acceleration actually has a positive displacement, right? We can see that from that graph. Okay, well, I hope that that makes sense. Okay, to use expressions in terms of sum or of m, a, and y. What is m? M is the mass, a is acceleration, expression for acceleration, and y is expression for the amplitude. Okay, so for this question, I've been asked to find omega. Okay, but I know essentially that omega acceleration are related by these following equation, because I'm asking myself, a stands for acceleration, y stands for displacement x. I have omega in the middle. What connects these things together? Ask yourself these critical questions. I have this, I have that. How are all of these things connected? Sort of like a little puzzle, right? So in order for me to find omega, I'm just going to say omega squared is going to be negative a divided by x. Okay, so pick an a, pick an x. Let's get along with it. So omega squared is going to be equal to, so I'm going to go crazy and pick 2a and negative 3y. So my acceleration is 2a, and my x is negative 3y. Omega square root of 2a divided by 3y. That's it, you're done. So it's going to be the square root of 2a divided by 3y. You got it. Move on to the next question. The maximum speed v0 of the oscillations. What is an expression for speed in simple harmonic motion? V is going to be equal to plus or minus omega, the square root of x naught squared minus x squared. The maximum displacement, if you have the motion of something, maximum displacement only occurs when you're exactly passing through the origin. Right? When you're passing through the equilibrium point, that is when you're going to have the greatest velocity. It's only when you pass through that point. So if I want to describe the system, I can bet that when x is 0, that's when I'm going to have the highest speed, as you can see over there. But it's going to come to rest on that side, then have the highest speed when it passes through the center. So when x is 0, the square root of x of that squared, my v is going to be equal to my omega x naught, essentially. So I'm going to say what's my omega? The square root of 2a over 3y. So I'll just have root of 2a on top of there times 3y over the square root of 3y. And if I look at this, this is root of 2a. This is 1 to the power of 1. This is 4 of half. 1 minus half times the square root of 3y. Add these two guys together because root of a instead times root of b. Just going to be root of ab. Okay. So if I go here, I'm just going to say, here's going to be the root of 2 times 3 times 6. So it's going to be 6 ay, right? So that's going to be my final v naught. It's going to be the square root of 6 ay. So I know that for oscillations, my total energy, the total energy E, right? Think of kinetic energy. Kinetic energy is maximum at equilibrium. But if, for example, if you have an oscillating system, the EP at equilibrium is 0, right? The EPE, the elastic potential energy, is 0. If you have a pendulum at equilibrium, the gravitational potential energy itself is 0. So always at equilibrium, the potential is going to be 0. So if I have in this specific scenario, at equilibrium, my total energy is just going to be my kinetic energy, which is half mv squared, right? But my v, I know it. My v, I know that it's omega x naught. So my maximum acceleration would just be 1/2 m omega squared x naught squared, right? So it's going to be 1/2. I already know my m. I already know my omega, which is 6 ay, because it's all of that squared. For my omega, I'm going to put, remember, omega is root of 2a over 3y. Okay, so it's going to be square of that squared. It's going to be 2a divided by 3y multiplied by 3y squared. Okay, so it's going to be half and half. That's going to cancel out. That's 3 squared 9, 2 by 2. So it's going to be 3a my. 3a my. Right, 3 a.m. Why? I don't know why. Okay, it's just 3 a.m. That's why. Hope you get it. The period of oscillations is 0.75 seconds, and the value of 3y is 1.8. Right? Determine an expression for x in terms of time t, where x is in centimeters, t is in seconds. Okay, so let's think about this. I have x, I have t. I want to find the relationship between these two things. What do? So essentially, if I look at this, I'm like, x and t. What equation comes to mind? Oh, x is equals to x naught sine omega t. Now, this is not going to be intuitive, guys. Under real actual examination conditions, this might not be easily accessible at your fingertips. So you really need to study and have a lot of things at your disposal to say, I'm looking at an expression, I have the value of x, which is my displacement, I have t. Sit down, write and jot down all the formulas you know that relates x and t. And it's going to come up to you eventually that, oh, this is the formula that I was supposed to use. Intuitively, it might not come right away, but if you give yourself enough time, you will be able to find out, okay? So in this case, to find omega, I'm going to say omega is going to be 2 pi divided by t. So my 2 pi divided by my time, which is 0.75. And if I do this, it's going to give me 8 over 3 pi. Okay, so my x naught, I already know it's 1.8, and 8 over 3 pi is like 8.4 or something like that. So it's going to be x is equal to 1.8 sine 8.4 multiplied by t. So here I can just put 1.8 sine 8.4 multiplied by t. Hope that makes sense. Okay, next point. Define electric potential at a point. You have a specific point, right? A tiny little point, and you want to find electric potential. You want to define electric potential, let's say, at that specific point. So what is electric potential? It's just the work done per unit charge. Okay? So it's the work done per unit charge in moving it from infinity to the point. So I would rather prefer you say per unit positive charge. That's electric potential. So imagine you have a positively charged sphere. So in this case, this could be my positively charged sphere. And I have a small little positive sphere. And we know that like charges don't like each other. So I'm going to have to do work to move towards that thing. And as I'm doing that, I'm actually doing work. The work that is being done is actually being gained by the positive charge because I have to literally push it. So it's gaining that work. I'm doing work. The work done per unit positive charge is actually the electric potential. So that when it's very close to the positive charge, it has a lot of potential. And if I just leave it, it's going to get repelled so much by that potential. It's going to move away. And because of that, I can therefore say I've utilized all that energy, right? And if I had a negative charge, and so I'm getting attracted, I'm actually losing energy. So my potential work done would just be negative, right? And so forth and so on. B, two isolated charged metal spheres, X and Y, are near each other in a vacuum, okay? The centers of the spheres are 1.2 meters apart as shown. 1, 2, okay. Potential against displacement X, we're given this specific system, okay. State 3 conclusions that may be drawn about the spheres from Fig 5.2. The conclusions may be qualitative or quantitative. Okay, let's go about it. So if I look at this graph, I see something very peculiar, right? First, let's start with the almost doable one, the one with regards to radiuses, right? So inside a sphere, something special happens. Inside a sphere, something special happens. If you're looking at here, all right, something special is going to happen. So what's happening? What's really happening? Right. If you have a sphere, let's make it bigger. Right. If I have a sphere like so, okay. Inside this sphere, charges are evenly distributed, right? So it's an assignment that we make. If it's positively charged, this conductor itself is positively charged. If you take a small little positive charge that knows no sin, place it on the middle, it's not going to move. It doesn't matter how positive all these things are. They could be negative as well, right? You have a lot of people, a small little cat in the middle, and everyone wants that little cat, right? No one is going to be able to get it because everyone wants it. They're going to fight each other on their own. So that implies that essentially because these things are all repelling right? This one is saying I don't want you, it's repelling like this. This one is saying I don't repel you, it's repelling like that. Everything is just repelling all at the same time, all at once. This thing is not going to experience a net resultant force. So the force is zero when we're inside the sphere, because the charges themselves are going to cancel out. There's another complicated way to explain this, Gauss's law and all of that. We won't get much into that, but a simple understanding, inside the sphere, the force is zero, because everything is just happening to me all at once. And the work that is done to move something inside the sphere is not necessarily that much, because it's just standing at that point. It has a potential. Remember, it's standing in the middle over there. It has a potential, because potential work has been done to let it stay at that point from infinity. But essentially, it's not doing any work, because it's not moving, it's stationary, right? It's not doing any work. It has potential. Remember, potential is zero at infinity, but anywhere else, potential has an actual value. So if there is potential, but it's not changing because this thing is not moving, that means the potential itself will be constant, right? That's a little bit of something difficult to unpack, but I hope that it makes sense, right? So if I have these graphs where I've been given a potential graph against that inside the sphere, I know that no work is done inside the sphere because the potential is constant. The work done is constant. So for this sphere, which is sphere X, right, sphere X is going to have a radius of, in this case, 0.3 over here. In this case, it's going to be 0.1. But from here, it's 1.2, 1.1. So this gap is going to be 0.1. Okay, so X, the radius of sphere X, 0.30 meters. And the radius of sphere Y is 0.10 meters. First point. Let's move on. Is the charge on one thing positive? Is the charge on one thing negative? Okay, let's talk about it. I love charged spheres. They're so cool. Why am I gonna say this? Right? I'm gonna explain a little bit of something here. Let's assume you have a person who's standing over there, right? Let's say the person is Bob for all we care. And then there are two things, X and Y. Let's assume there are two people who hate Bob, right? Maybe the people that he learns with, right? Let's say the ladies that he learns with in his class. A lady at X, a lady at Y. Both of them hate and despise Bob, right? So we can assume that as Bob tries to move towards sphere X, because the lady hates him, there's going to be a force, right? A resistive force. The person's going to say, no, I don't want you. And Bob is going to be pushed away, right? But as he tries to get closer to that, Bob is also going to be pushed away. So he's always in this indecisive mode, right? No one likes him. No one likes Bob. Who does that, right? So he's always in a mode where he gets pushed over there, he gets pushed over there, he gets pushed over there, he gets pushed over there. That's not fair, right? No one likes Bob. Maybe something's wrong with him. Who knows? So if I were to place Bob at P and allow Bob to move to Y, the work that Bob needs to do to move away from X, let's say X is Susie, right? The work that Bob needs to do to move away from Susie is actually less, right? If someone hates you, it's very easy for you to move away from them. They start talking, you just walk away, right? So the work that you need to do to move away from X is actually going to decrease over time because it's a person that you hate, right? Or they hate you. Vice versa. But as you try to approach towards, let's say, Sarah, which is at point Y, who is at point Y, you have to do more work. A person doesn't like you, you have to do more work. You see them, you have to overcome that, use that willpower, you have to buy them flowers, you have to do all this, but they hate you. So you do more work as you move towards Y, right? I can make a whole video about this if you want to, just put in the comment section. But essentially, if X hates you as P, as a particle at point P, that implies that X is positively charged because I'm placing a positive charge at point P. You might be wondering, why am I placing a positive charge at point P? Essentially, we always work with positive charges in physics. Probably when this topic was discovered, electrons weren't much of a thing. I would like to believe so, right? So I'm looking at this scenario here. I'm saying, interesting. I'm at something at a certain potential, right? A certain level, right? Potential over there. And then I'm starting to move. Because I'm moving away from you, like so, my work is less, right? My work is less. I just hit a point over here. But I'm now moving towards someone who hates me. my work begins to increase. But this is my work done, right? My work begins to increase because the person does what? The person hates me, right? Which is very sad. Who would hate Bob? Nice person. So I can therefore just tell both X and Y are positively charged. And this is understandable because the only thing that hates a positive charge are both positive charges. They're the only thing that allows repulsion to occur between X and that proton, and Y and that proton. It's only something that's positively charged. It'd be a little sneaky, right? And write both of them as points, right? It's a little secret, right? Just write charge on X is positive. Okay. So now I want to move something somewhere very interesting, right? And you can see the differences in potentials. You might be wondering, one is a bigger potential than the other, so they have probably opposite signs. No, one is just having a bigger radius, right? So the other one has a smaller radius, so it's going to have a higher potential because you're going to get so closer to the center. The distance itself from P to the surface of that is going to be very big because simply it has a higher potential. So if you're going to get closer to here, let's assume I have something over here, right? And I were to get to over here, right? There's going to be a higher potential. There's going to be present over there. So the minimum turning point should always be at the midpoint. So in this case, the midpoint is 0.6. If I were to draw a tangent over here, the gradient is 0. So it's only here at 0.6, which makes sense, right? 0.6 over here, 0.6 over here. So it tells me these two things have the same charge. Why? Because for me to do work to move away from X, I reach a point where it's the midpoint for me to do enough work to move towards Y. So it tells me the two charges of these things are the same because it's only at the midpoint where I have the same separation from the center of X, 0.6, same separation from the center of that, 0.6, and that tells me from the formula Q over 4 pi epsilon r, from Q over 4 pi epsilon r, it's only at 0.6 where you have the same distance and the same distance where you have a potential of 0. If you add the potential of one graph and the potential of the other graph, you have the lowest possible potential only at the midpoint. And that only occurs if the two charges are equal. If it wasn't equal, the turning point would occur somewhere closer to that other sphere. So, or when E is equals to 0, occurring at the midpoint, because essentially it tells me that the force is 0 at the midpoint. And that only occurs, right? V0 when the potential gradient, remember E is the negative potential gradient, so the gradient of this specific thing, negative potential gradient. So it tells me that at the midpoint itself, E is 0. The electric field strength is 0, and that's very, very important for me to be able to be thinking of because of that fact, right? If E is 0, it tells me I'm at the midpoint. So the magnitude of charges on the spheres are equal. Okay, a proton is held at rest. Remains at rest. That's a smart choice. I would do that if I were me, right? Remains at rest. And why is that? Because there is no resultant force. The electric field strength is 0. The gradient, remember, the electric potential is 0, right? Like I said, the potential energy is already this minimum, right? I don't have enough energy to go towards that. I don't have energy to go towards that, right? Because the resultant force experienced I hope that makes sense. Moving on. Question 6. Two capacitors X and Y are connected in series to a power supply is shown. The capacitance of X, Cx, the capacitance of Y, Cy. Derive an expression in terms of Cx and Cy for the combined capacitance Ct of the capacitors in your circuit. Explain your reasoning. Okay, let's rush through this and let's get it done. So, for capacitors in series, what do I know? I know that the total potential, right? Famous guy Kirchhoff came up with these laws, where Kirchhoff's laws, okay, so Vt is equal to Vx plus Vy. The total potential, energy, the total potential is going to be Vt, electric potential is going to be Vt, it's going to be Vx plus Vy. But what do I know? I know that C, okay, but C, let's do this a little bit faster. C is equal to Q over V. Right, equal charge on both capacitors. Right, we definitely equal charge on both capacitors, so V will be equal to Q over C. Right, So if I go on this side, I have Q over C total is going to be equal to Q over Cx plus Q over Cy. So 1 over Ct is going to be equal to 1 over Cx plus 1 over Cy. The capacitors P and Q are connected in parallel to a power supply of voltage V. The capacitance of P is 200 microfarad. The capacitance of CQ can be varied, can be changed between 0 and 400. So I have a capacitor P in Q. But Q has a certain property. It allows its capacitance to be changed between 0 and 400. So it varies, you can pick whatever you want. So when CQ is 0, so if I were to connect them in parallel, what would I do? Right? Take my circuit over there, 1, 2. Take my circuit over there, 1, 2. Connect them over there, put it like that. That's the spirit. That's the spirit. Okay, so this is going to be CQ. And this is going to be CP. Right? Let's get creative with this. Okay, so I want to show that the supply voltage is 5.0. What do you think I should do? I've been given total energy. I've been given total energy over here. Look at this. The total energy that is stored in the capacitor is 2.5. What should I do? What connects all these things? You ask yourself, what is energy? I know that energy for a capacitor is going to be 1/2 times Q times V. Right? If you have a Q against V graph, the area of this graph is going to be your energy. Okay? Now, I then wonder, and I ask myself, what is Q? Right? Q essentially is just C times V. So my energy E would just be equal to 1/2 multiplied by C V squared. So this is my expression for energy whenever I have a capacitor question. Always start from saying 1/2 Q times V. Where does it come from? Work done is actually the work done per unit charge is V. So Q times V is going to be your work done. And then essentially your work done is going to be Q times V. But not all the energy is stored in the capacitor. In fact, half of that energy is stored in the capacitor. The rest is used in overcoming resistive forces, especially in the I would say resistance, used to overcome resistance inside the battery itself. So internal resistance. So you're going to end up with 1/2 QV. That's all sort of where it comes from. But essentially, all you need to know is C is equal to 1/2 QV. So E is equal to 1/2 CV squared. So you want to find V in this specific question. What you're going to do is you're just going to say V is going to be equal to 2. So just the square root of 2 times E, which is 2.5 times 10 to the power of -3. Divided by your C capacitance is 200 times 10 to the power of -6. So your V is just going to be equivalent to 5 volts. Punch it all that in the calculator and you will get 5. Okay. And then if I look at the next question, I'm asked to calculate the total energy in millijoules that is stored when the capacitor has maximum value, right? So if I think about this, I want to find the total energy in millijoules stored when the capacitor is its maximum value. So if I'm like this, I'm like, what's going on? I'm a little bit confused. And I just draw my little circuit over here. Remember, the same circuit that we draw right over there, right? Like this. So this is CQ. This is CP. And whenever things are in parallel, you add their capacitance, right? So low for series, low for parallel. If you want to have some fun, try to derive it, right? Try to say inside these two things, V is the same. Then use the relationship C is equal to Q over V and try to prove that the total capacitance is the sum of the individual capacitance. It'll be a fine challenge. But essentially, if I don't find the total energy stored in the capacitor when it has its maximum value, all I just do is I say, what's my total capacitance? What's my total capacitance? That's the question I'm asking myself here. So my total capacitance will just be equal to 200 plus 400. It's going to give me 600 microfarad. And my total capacitance will just be 1/2 times 600 times 10 to the power of -6 times my V, which will be 5 squared. Punch that all in the calculator and you get 7.5 millijoules. Very important. 7.5 millijoules. Next question. On Fig 6.2, sketch the variation of the total energy E stored in the capacitor with CQ, as CQ is varied from 0 to 400 microfarad. Okay, so I could create some complicated mathematical relationship, try to evaluate, blah, 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 blah. But what I could do is find points. For this one, I'm feeling a little bit lazy. And I'm like, when C is 0, I've already been told my total energy, guys. You're given when CQ is 0. The total energy is 2.5. Be a little bit lazy sometimes. Right, get 2.5. So I go here and I say, at 0, when CQ is 0, I have 2.5. That's a coordinate. And then at 7.5, I have 400. At 400, I have 7.5. Be a little lazy. So now I just need to find the midpoint. If I can find the midpoint, I can sort of establish a relationship. So I can say ET is just going to be equal to 1/2 CV squared. So if I want to find my E, when my C is 200, it's just going to be 400 in total times 1/2 times 5 squared. And this, if I punch this, the calculator gives me 5.0 millijoules. Okay, just give me 5.0 millijoules, which is just the midpoint, which would be over here. So to connect all of this together, it's just one straight line like so. Like so. And that'll be it. Okay. Faraday's law of electromagnetic induction. We've been asked to state Faraday's law of electromagnetic induction. What does it say? It tells me that the induced EMF, essentially, it tells me that the induced EMF is directly proportional. What is Faraday even saying? Right? I don't even understand what Faraday is saying. Okay, so we have what we call induced EMF, right? Made up of two words, induced and EMF. EMF is just a potential difference. Electrons can accumulate on one side and not be on another, and there can be an EMF that's present. So with microfaraday, what microfaraday is essentially saying is saying if you take magnetic flask linkage, right? Magnetic flask is the flow of magnetic flask lines. So if I were to take in magnetic field lines and create a little bundle, right? So for example, if I have these field lines, right? These magnetic field lines, and create a little bundle of them, and if these were to flow through a certain area, I would essentially, that's magnetic flask. Flask just refers to how something flows into a certain area or through a certain area. If you open a door and people start flowing into that door, I could say it's people flask or something like that. So if magnetic flask starts flowing, I say it's magnetic flask. It only becomes linkage if you put multiple turns, multiple coils that links those things together. So if you have something else that then comes and cuts those magnetic flasks, the electrons that are inside that thing experiences a Lorentz force. They experience a force, and because of that force, they're able to move. And as they move, they've induced an EMF, right? So I had magnetic flask field lines that were just flowing, and those field lines were able to create a magnetic force because those field lines interacted with the moving current, interacted with the moving electrons, and because of that, as the electrons began to move, an EMF was induced. That's my little bit of my understanding of microfaraday and what it was saying. Again, if it doesn't make sense, I'll put it in the comment section and we might work on it. So the variation of flask density, right? Flux density, phi is equals to B times A, right? F is equals to BIL. So some of the formulas that you should be aware of. So I'm given that graph, and I've been asked to calculate the maximum magnetic flux through one turn of the coil. How many? If I were to bundle up those magnetic field lines, they create a little bundle that's going to have a magnetic flask. So phi, magnetic flask phi, multiplied by A, flask density, multiplied by area. And the maximum flask density from the graph, guys, let's look at it. It's going to be 7.2. If I look at this, 7.2, 7.68. Right, so it's going to be 7.2 for my B. And my area is 3.2 times 10 to the power of negative 4. So my that is going to be 2.3 times 10 to the power of negative 6. 2.3 times 10 to the power of negative 6. Okay. Determine the maximum rate of change. Look at this. Rate of change of magnetic flask linkage, right? Rate of change of magnetic flask linkage. Okay, that's a little bit of a rhyme there, right? So I want to find the rate of change of magnetic flask linkage. Okay, so if I look at this graph, right, the rate of change tells me gradient somehow. Where do I get the biggest gradient possible? Just draw tangents, guys. Anyway, so if I draw a tangent here, draw a tangent here, draw a tangent here, draw a tangent, where am I going to have the biggest possible gradient? So the biggest possible gradient is going to exist right over here, right at the turning point. That's where I'm going to have the steepest gradient possible. So if I were here, right over here, at this point, that's where I'm going to have the steepest gradient that I can possibly draw. Okay, so something like this. Right, something like that. Okay, so my goal is now to just find the gradient of that specific line, and I'll be done. Okay, so all I need 2 points. Once I have those 2 points, I can then be able to find that. So just draw a tangent, take 2 points. So if I'm to be a little bit creative over here, although it might not necessarily be accurate, right? So after I've drawn my tangent, I can't really see clearly and get accurate points for you guys. If I were to do that, I would be lying. So as you can see, you can just draw a tangent over there. And if you draw a tangent, you're just going to take 2 points, right? You take 2 points. So if you have an actual physical paper, that would be much better, much useful for you to draw that line. If you don't have, when an actual exam comes, be able to do that. So I take 2 points. And if I were to take 2 points, x1 and y1, right? And okay, once I have those 2 points, I can just calculate my gradient. Then after I've obtained my gradient, I now know that my gradient is change in B divided by change in time. But my magnetic flask linkage is just my change in B divided by my change in time times N times A. But my A is 3.2 times 10 to the power of negative 4, right? And I know my N, I can therefore be able to find my E. And if you do all your calculations correctly, you get about 0.82. Or less or more, just depends. But what's important is the philosophy. What's important is the answer. Draw a tangent, take 2 points. After that, then use delta B over delta T times N times A. Then you've asked to state the maximum magnetic EMF V naught, and used across the coil. That maximum rate of change of magnetic flux linkage is actually going to be your maximum induced EMF. Because remember, to find EMF using magnetic length of Faraday's law is just the change in magnetic flux linkage divided by the change in time, and that's exactly what you were finding. So your V naught would just be the answer that you have obtained above. And then sketch the variation of EMF V induced across the coil with time t from t is equals to 0. So when t is equals to 0, I'm going to have a gradient of what? Remember, your gradient multiplied by n multiplied by BA, or rather, your gradient multiplied by n multiplied by A is going to be your induced EMF. So if I'm looking at this specific scenario, if I'm here, I have the lowest possible gradient. My gradient here is 0. So that tells me that the EMF that I'm also going to have is going to be 0. Okay? So the EMF where I'm starting here is 0. So wherever I have a gradient of 0, I'm going to have a corresponding point that's going to be 0. And I'm seeing that at 0, I'm seeing that at 1, I'm seeing that at 2, I'm seeing that at 3, I'm seeing that at 4, I'm seeing that at 5, and I'm seeing that at 6. And then my gradient is going to increase and become a maximum. So first I have a positive gradient over here, and my gradient is increasing, becoming steeper, then it decreases, and then it reaches 0. The same happens, then it does that and that and that and that. And therefore I can sort of predict, right? Remember, according to Lenz's law, the direction is supposed to be an opposite. It's supposed to have a negative, right? So I'm going to start off by having a change in gradient that's like that in the negative direction, really. But the direction really doesn't matter that much. I've tend to realize the direction doesn't really matter, but rather the philosophy itself behind it. So something like this. But essentially what you're supposed to plot, something like that, right? It's a little bit crooked, but that's what you're going to plot. And then the variation with V with T can be described by the following equation. Determine the values of A and the values of B. So I know A is my maximum amplitude because it's a graph of sine, but it has had an amplitude of V naught. So it has been, it has a certain stretch factor that has caused it to be elongated in the y-axis. So I can basically describe my stretch factor as V naught. So I can just say A is going to be equivalent to V naught, where I know V naught is 0.82, guys. So I can just here have 0.82 in volts. Then for B, I know B is just my frequency for this specific thing, omega, which is just going to be equal to 2 pi divided by T, right? Which is just going to be 2 pi divided by 2.0 times 10 to the power of negative 3. That's going to give me 1000 pi. But physics, they just love decimals. They can't get enough of them, or actual answers, not necessarily exact answers. So in this case, to 2SF, it's going to be 3100. You can write it as 3.1 if you want, but it's just 3100. And my units are going to be, remember, it's omega, and the units are rods per second. Okay, astronomy and cosmology. Number 8. I'm given part of an emission spectrum of visible radiation emitted by hydrogen gas in a star of a distant galaxy. So I have a galaxy and I have a little star that's present in that galaxy. Okay, and that is going to emit a certain visible radiation that I'm going to see in a lab by doing the same experiment, but this time using hydrogen gas. Now we know that I have Earth and I have this galaxy and it's moving away from Earth with a specific velocity. Okay, and I want to explain how the position of the lines that be present on this emission spectrum as seen by an observer would differ from the positions that are shown over here, right? Okay, I just want to explain how they would differ. So I know if you're moving away, right? I've been given a hint, it's moving away, and the moment it starts moving away, redshift occurs. It's going to appear to be longer than what it actually is. So the movement of star causes redshift. Okay, as the star is moving, the light becomes longer and longer and longer, shifts towards the red region, and it's going to be redshifted. So I can just say movement of star, right? Because as the star is moving away, it's going to have light that it receives, light that we receive, is going to be redshifted. It's going to shift towards the red spectra when these kind of graphs are being plotted. So now how would these position then see? So what I will now be observing is going to be an observed frequency that's going to be lower than the emitted actual frequency because of redshift. So the positions are going to have a lower frequency, right, than the actual emitted frequency. That's the explanation, right? So the observed. Now if I were to go on this graph and look at it and say, how am I going to plot, because I've been asked to draw 3 possible lines seen by the observer. So it's going to be to the left because of redshift, right? It's going to have an observed lower frequency, like so, like so, like so. Okay, a little bit, my apologies for the squiggly lines, but essentially this x must be the same. If you were to draw your lines, this distance between these two things must be the same, because the entire graph is going to be shifted because of the redshift, right? So it's going to just be translated as it is. Okay. The lines in figure 8.1 correspond to electron transitions down to the energy level negative 3.40. One of the lines represent emitted radiation of wavelength 488. Calculate the energy of the photon of this radiation. I have an equation for energy. I know E is equals to hc over lambda. So my h is 6.63 times 10 to the power of negative 34. Is that all in your calculator? You get 4.08 times 10 to the power of negative 19. Okay. Determine the energy in electron volts of the energy level from which the electron transition originates to cause the emission of this radiation. Right, what's going to happen here? So you're going to have a level, right? Let's say a level like this. You're going to have another level, let's say a level like this. And you're going to have a little electron over here that's having the time of its life. Right, your electron's over here having the time of its life. Now it wants to transition. So it wants to transition down and go to this specific orbital. Okay? But in order for it to do that, it has to lose energy. It doesn't make sense for it not to lose energy because it has to transition from one orbital to go to another orbital. If these were houses, if these were classes, you have a high income class for people who are rich. We have Lambos, we have money, we have all of that. If they were to transition down and go down to a state where they have no cars, they have all of that, they have to give something away. They have to get rid of all of that flash, fame, and everything that they have. So in a similar manner, if you have an electron that is at a certain energy level, leaving at a certain energy level that I call X, and it wants to drop down to an emission that's going to cause this to occur. And so I already know that this is negative 3.40. It originated somewhere and it dropped to negative 3.40 EV. How did I know this? I was told, guys, I was told that it's at a transition downstream energy level negative 3.0 volts. But in order for it to do this, it's going to have to give away energy. Right? It's going to have to lose money. It's going to give away energy that is of this photon energy. This is the photon that it's emitting, that is that specific amount of energy. So if I want to find the energy of each specific photon, it's just going to be this converted to electron volts divided by 10 to the power of 6 times 1.6 times 10 to the power of negative 19. So if I just want to transition this to electron volts, and all of that is going to just give me I would say 2.55 approx. So I'm going to lose 2.55. What did I start with? Remember, these things are negative for a reason. Right? They're sort of made with the intentionality of saying you approach zero. Right? What did I start with? Okay. So it tells me if I were to add these two up, I'm going to have negative 0.85. Such that if I lose, I get negative. It's like a credit, guys, right? It's a debt. Okay, think of this as a level of debt. If you're in position A, you owe people, right? You have all these Lambos and all of that, but you have a loan of negative 0.8. But because I had a loan or I had debts before, if I'm going to transition down, I'm going to lose and get more of it. I'm going to get more into debt. I'm going to get more negative. So the more I transition down and down and down, I'm going to get more negative. So if I want to find out how much money did I lose, I have to say, okay, I have a credit of negative 3.40. But what did I even start with if I lost 2.55? I have to go back and get negative 0.85 so that if I lose 2.55, I'm going to end up with more negative answers, which are negative 3.40. Move on to the next question. Determine the wavelength in nanometers of this radiation as detected by the observer that is on the Earth. So I want to determine the wavelength of this radiation as the observer detects it. Right? I have an equation that you can find in your formula booklet that relates the equation. We could work it out, but essentially it says that V over C is the change in lambda divided by lambda. So the speed of the moving star divided by the speed of light is equal to the change itself in the wavelength divided by lambda. So if I want to find change in lambda, it's just going to be my V, which is in this specific case 6.2 times 10 to the power of 6. I'm already given this, guys. 6.2 times 10 to the power of, where is it? 6.2 to the power of 6. You see that? So I'm already given that, and my galaxy is moving away like so, and I want to find the change in the observed frequency by that observer. So V over C, 3.0 times 10 to the power of 8 times my lambda. In this case, it's 488. 488. And this is going to give me 10 nanometers, right? So I want to determine the wavelength that was detected by this individual. If the change is 10 nanometers, it simply means if you started with 488, in order for you to be redshifted, you're going to detect something that is longer. that is a higher rate shift, plus 10, that's just going to be 498. So 498. Okay, Hubble. What is Hubble's deal? Edwin Hubble was a very smart guy, did a lot of astronomy work, and one of his famous works is called the Hubble's Law. What does it state? It says that the speed of the receding galaxy is directly proportional to the distance in which it's moving away. Right? So I have the speed of recession of a specific galaxy. So the assumption is, in the entire world, galaxies are moving away from each other, right? They're drifting apart, they're sort of moving one away from each other, right? And there's a certain distance between these two galaxies, and the distance itself is going to increase. So the further you are away from something, the faster that you're moving away, right? And this is sort of the basis of the Big Bang theory. Right? That's what the scientists claim. If you have galaxies that is expanding, essentially it's the galaxies that are moving away from each other, you find that the galaxies at the edge of the universe are moving a bit faster than the galaxies that are closer to us, relative to us as Earth, in such a way that the whole Earth, or rather the whole universe itself, begins to expand. Right? But essentially that's Hubble's law. V is equals to h naught over d. So if I want to find the distance from the galaxy to the Earth, and I have the Hubble's constant, it's just a matter of making d the subject of formula, 6.2 times 10 to the power of 6 divided by 2.3 times 10 to the power of negative 18. The value of d that I get, 2.70 times 10 to the power of 24. State what is meant by binding energy. State what is meant by binding energy of a nucleus. Okay, if this is confusing you, I just want you to watch just a 1-minute video, less than 2 minutes, that's going to explain binding energy a little bit better. But if you to understand binding energy, it's just that you have a nucleus and you want to separate all the constituent elements of a nucleus to its, constituents. Just separate them to get to infinity. And the whole point of that is to say, for example, if you have a burger, you want to separate it into the buns over there, the lettuce over there, the tomatoes and everything. You just want to separate them. And the whole goal of that is really you just want to separate them, right? So binding energy is how much energy do I need to separate all the nucleus, the nucleons of a nucleus to infinity, right? So the energy required. Okay, so if I'm given table 9.1, that shows now the masses of two subatomic particles, a proton and a neutron, and I've been asked to find the mass defect. So the theory is, guys, these things, some of them are a little bit abstract to understand, but the theory is, if things are separated, they weigh more than if they were combined. Okay? And to be honest, it's just to say, if you have a human, right, and if you're to separate the arm, the body, and all of that, put them aside, weigh that's going to be heavier than if all of them were to be combined together. It's a little bit tricky to understand, guys. I've tried. But the law is to say, some of the mass is, it's a bit tricky to understand, but the law is to say some of the mass is converted into energy when things are bonded together. If you bring things together, some of the mass will be converted into energy. So if I have a polonium that is over there, how many protons does it have? How many neutrons does it have? So it's 84 protons times 1.00. So I can say my delta M is essentially my mass when they're separated minus the mass of the nucleus itself. So the mass when they're separated is 84 times 1.00, 276 minus 128 times 1.008665. If I subtract that, if I add this to U, right? And you know U is actually 1.66 times 10 to the power of negative 27. Okay, so then I subtract 211.942749 U, where U, so just substitute U with 1.66 times 10 to the power of negative 27, and you end up with a mass defect of 2.95 times 10 to the power of negative 27. I want to find the binding energy. So the binding energy will not just be my mass defect because that mass defect went to contribute to the binding energy. So the binding energy is going to be my mass defect times c squared. Right, so if I do that computation, find the mass defect times c squared, and you get your binding energy. If it's now the binding energy per nucleon, take your binding energy, divide by n, and you get your binding energy per nucleon. So it's just your binding energy divided by n being the number of nucleons. So we want to find how much binding energy was contributed by each nucleon, or went to each nucleon. So divided by 212, 1.25 times 10 to the power of negative 12. Okay. On Fig 9.1, sketch the variation with nucleon number A of the binding energy per nucleon for values for A is equals to from 1 to 250. So essentially, I know that ion is the most stable. So if I'm over here in the middle, that is where I'm most likely to find ion, Fe, with sort of like 56. So the rule is the binding energy itself, the stability, actually increases as you have small things that build up and build up and build up. What's the theory? If you have one person that's holding hand with themselves, they are very stable, they're on their own. If it's two, the bond is stronger. If it's three people, more stronger. If it's four people, stronger. 5, stronger. 6, stronger. 7, 8, 9, 10, 11, 12. Gets stronger and stronger and stronger and stronger and stronger. But it reaches a point where it's too much. You have too many people and it starts to break down. So the more they become, it's harder for you to say if you have 20 people and you ask them to make a network, a structure. It's just easy if you disentangle one person for the whole thing to collapse. So the bigger the AR, the bigger the atomic mass that it has, the bigger the nucleons, the more unstable it is. If you just remove one thing from that, it easily collapses and decays into something stable. But if you're below that, if you have 2, 3, 4, 5, and they get beat up and beat up and beat up, they get more and more stable. So over here, it's going to increase like this. So over here, it's going to increase, right? There's sort of some little things over here. Reach the maximum at ion, and then it's just going to go like so, right? So it depends on how you structure it. Essentially, that you're looking for, right? So Cambridge just looks for a line that's rising by a single peak, right? That is just the left, and then it continues positive gradient on that side, then negative gradient on this side, and you'll be fine. Draw an X to show the position of polonium. So because polonium is 212, so I really expected to find, I wouldn't find it anywhere except here. So I'm just going to put a little X. X marks the spot. Polonium is a radioactive isotope and undergoes alpha decay. If you've done AS, guys, know the equations for alpha decay. You've done AS before. So I just explain with reference to Fig 9.1 why the alpha decay of polonium results in a release of energy. Why does it result in a release of energy? So this alpha decay, right, forms 208 and 82 of X, right? So this thing is has a lower nucleon energy. So the product of this reaction actually has a lower nucleon number. So if I look at this, it says 208. That nucleon number is actually lower. So because of that, I want to explain if there's going to be a result in energy. Is it going to be stable? What's going to happen? So because the nucleon that has been formed has a lower nucleon number, I had 212 over there. I have 208 over there after alpha decay has occurred. The nucleus formed, we have a greater binding energy per nucleon because it's going to be up here, right, where it has a greater binding energy per nucleon. Okay, and that's important, and I want to discuss why. Right, so if you form something that is a lower nucleon number, right, we expect the thing to be more stable, simply because it has a greater binding energy, right? So a greater binding energy tells me that that thing is going to be more stable, right? Why is it more stable? Well, it's essentially because it has to release energy, right? As you get closer to iron, your stability increases, right? So it becomes more stable simply because it has a greater binding energy. So something has a lower nucleon mass, is a lower nucleon number, and it's going to have a greater binding energy. that means a lot of energy is going to be released because the reaction is more favorable. Okay. Last question, question 10. Then we'll be done. Describe how reflected ultrasound pulses may be used to obtain diagnostic information about internal structures. What is ultrasound? Ultrasound is a very high, I would say, form of sound, right? With infrasound, ultrasound, and sound that we hear. If sound is below 20 hertz, we can't hear it as people. And if sound is above 20 hertz, above 20,000 hertz, we can't hear it as well. It's called ultrasound. And some smart people actually found a use for ultrasound, which is to be used in medical diagnostics. So if you've seen pregnant ladies, if you've gone to prenatal scan, you've probably seen these big machines that they use. They rub jelly on the baby, and they get these beautiful photos, which are just, scans that show how the baby is behaving. So basically the principle for operation is ultrasound. And how it works is that an ultrasound beam is sent, enters through the skin, then it reaches a boundary. Right? The moment it reaches a boundary, it gets reflected. And the moment it gets reflected, there will be a detector, a piezoelectric transducer. It's just something that vibrates. Condensating crystal, as the crystal vibrates, it just falls in the ultrasound range, emits frequent ultrasound waves. Then those waves, when they come back again, gets detected by the same transducer, and that same transducer then produces electrical energy. Okay, so because of that, I can then deduce diagnostic information about the internal structures that I've obtained. How? The intensity of the pulse that I get. Okay, so the first point is that the intensity about the nature of the boundary. So the intensity of the pulse gives me information about the nature of the boundary itself, right? So if the intensity is low, someone tells me something's off or something's happening with the boundary itself. Right? It could be the boundary between bone and tissue. You've reached the baby's skull, or something like that, where you have the bone and then you have the skull, and the intensity that I'm getting tells me how much is being transmitted, how much is being absorbed. I'm getting information about the nature of the boundary itself that separates those two things that I'm interested in. And then another thing is just the time gives information about depth of boundary. Okay, so I'm emitting something, then I'm detecting it, and the time itself tells me something about the nature of the boundary. So I arrive at a certain boundary, it tells me, okay, took me this long, then it calculates to then identify how deep the boundary is. So if it arrives at a tissue, then calculates how big is the skin boundary. It can do that through a lot of ways, but essentially by comparing the time, you can be able to get information about the depth of the boundary itself. Okay. Define specific acoustic impedance of a medium. 3 words. Specific acoustic impedance. So if I'm asked to define specific acoustic impedance, what do I say? Specific means, what are you talking about? Can you be more specific, right? In relation to medium, in relation to ultrasound. Acoustic relating to sound, and then impedance, resistance to motion. So specific acoustic impedance is just defined as the product of density and speed, right? So it's just the product of density and speed of ultrasound in a specific medium. There's a medium, and ultrasound is going to move with a specific speed, and essentially specific acoustic impedance is just the product of density and the speed of ultrasound in that medium. Okay. The last question, I've been asked to determine the intensity reflection coefficient for ultrasound that is incident on a water glass boundary. Okay, so I know that the intensity reflection coefficient is just essentially, I'll say, I need to first find the Z for water. So the Z for water is just the density of water times the speed of sound in water. And both of these information I am already given. So it's just 1000 times 1420. And this gives me 1.42 times 10 to the power of 6. Then my Z for glass is going to be my density for glass times my speed of sound in glass, which is going to be 2500 again, times 4560. That's going to give me 11.4 times 10 to the power of 6. So if now I want to find the intensity reflection coefficient, I know that is the ratio of how much ultrasound was reflected divided by the ultrasound that was incident. So if I have a boundary, ultrasound is going to be reflected. A certain amount is going to be reflected, and a certain amount is going to have been incident on that specific boundary. And the ratio that sort of compares that is the intensity reflection coefficient. So essentially how I calculate it is that I say Z2 minus Z1 squared over Z2 plus Z1 squared. That's going to be equivalent to just the difference, 11.4 minus 1.42 squared. Right, you can put times 10 to the power of 6 because they're the same, they just cancel out. Okay, 11.42, 11.4 times 1.42 squared, and all of that, punch that into a calculator, you're going to get 0.61. And then that would be your final answer. That's it, guys. So I really hope that this was helpful and you were able to understand a lot of things. And yeah, it's a lot of concepts really to understand and grasp in this paper. But if you just understand and master the basics, you can be able to pass it. And if you've watched until the very end, thank you so much. I do not know how I can be able to express my gratitude towards you. I really hope that you do well in your exams and that this exam and that this video was helpful. If there's anything that you'd like me to improve on, please do comment it. Thank you so much for watching. Please do subscribe and like and share it with other people. Thank you guys, and I'll see you in the next one.